How's everyone doing today? Doing good. It's kind of a dreary day, but doing all right. Not bad for a Monday, I hear that. Alrighty. So today we're going to look at, why does it do that all the time? Optimization. So maxes and mins of functions of two variables in this case. And in fact, optimization is what we're going to be doing all week. But we'll look at a different method of doing it in the next section. Okay, so remember, for functions of one variable, so if this is the graph of the function f of x, right? So it's the curve y equals f of x. Suppose we look at this, say from a up to b, doesn't really matter. But suppose we get something like this. Suppose this is a graph of our function on that interval. So remember, so we have local extreme values, which are if you're just looking nearby a point, say like right here. If we're just looking at points nearby, say we look at a little interval containing there, all the points on the graph are, let me do that. All the points on the graph near this point lie below it, right? So the value of our function is less than or equal to the value of the function at this point here. Let's call it like x1. So if we pick any point near x1, so any point x near x1, the value of the function is going to be less than or equal to the value of the function at x1. For all x near x1. In other words, in some interval containing x1. So we say that's a local max. Of our function there. And it looks like a little hill, right? If you just look nearby, it's the highest point of the graph. And then similarly, we have a local min here, and another local max here, another peak there. And notice that all of these guys, right, the tangent line is horizontal. But of course, so a local max and a local min doesn't have to be the absolute highest point. So a local max doesn't have to be the absolute highest point of the graph anywhere on here. And the local min doesn't have to be the absolute lowest. So for instance, here, this is the absolute lowest our graph gets. That's the global min, or the absolute min value of our function from A to B. And this would be the absolute max, and it's also a local max. But yeah, if you remember this from 140. Yeah. Also notice, no, so remember, so I was just about to mention inflection points. So remember, I think you mean critical points. Right, so a critical point is where your tangent line is horizontal. In other words, where the derivative of your function is 0, or it's a cusp or something where the derivative doesn't exist. So every local min and max is a critical point where the derivative is 0, but not every critical point is a local min or max. So for instance, here, it's supposed to be a critical point, like pretend the tangent line is horizontal there, or the derivative is 0. That's what we call an inflection point. It's neither a local min nor a local max, because you can find points where the graph is higher, no matter how close you look, and points where the graph is lower.
Points of inflection are found on the second derivative as well, right? Right, where you can see that there's like where it's positive and negative, and then you can see if it's okay.
Yes. Well,
right.
So yeah, we have a second derivative test where you can tell if a critical point is a local min or a local max.
Right. Yep. Okay.
Yeah.
Perfect. Thank you.
Yep. Okay. So that's the case for functions of one variable. It's pretty similar for functions of two variables, right? And we're going to focus on local extreme values today. But yeah, so suppose we have the graph of a function of two variables. Remember, that's a surface. The surface z equals f of xy. So I'm going to stick with surfaces that look like this because that's the simplest things I can draw. And they illustrate what local mins and local maxes look like. And in particular, this shows what a local min looks like. So let's look at let's say the point P here. Oh. Nope. There we go. Okay. So if you look at the lowest point on the graph here, the x and y coordinates, we'll call it, I don't know, A, B, but we'll just call it the point P for short. That is not working for me. Okay. So we say P is a local min, or a local minimum value for f happens at the point P in the xy plane. So that means if we look in a little disk around the point P and look at all the points inside that disk and look at all the points on the graph that correspond to those points, every point in there, the value of the function is going to be greater than or equal to the value of the function at P, right? P is like the lowest point on the graph. And so that's what local minimum values look like for functions of two variables. And local maxes are going to be sort of the opposite. Like local mins look like little valleys on our graph. And local maxes look like peaks on our graph. So let's give a proper definition for these. So we say a function f of xy has a local extreme value. So extreme values can be maxes or mins. It's just one word that covers both. So it has a local extreme value at a point P, which is the point AB. If there is a disk D about AB, and let me say about the point P, same thing though. So basically it's a technical definition, but like if you look close to the point AB, it's either the highest point of the graph or the lowest point of the graph. So for local max, if the value of the function at any point you pick nearby AB, it's a local max if it's the value of the function is going to be less than or equal to the value of the function at AB. So if you look at every nearby point and the value of the function is less than it is at AB, then AB is a local max, right? Like what we see up here. The highest point nearby on the graph. And local min is the opposite. If you look at every point nearby and the value of the function is greater than or equal to the value of the function at the point AB, then we say there's a local min at AB. Okay, so notice in both of these cases, let me sort of give myself some room here. In both of these cases, so for the local min, if we look at the tangent plane, I'm going to do my best. Oops. If we look at the tangent plane, for the local min, notice it's horizontal, right? The local min is the lowest point. The tangent plane is going to be parallel to the xy plane. It's going to be horizontal. Just like we saw for local maxes and mins for functions of one variable, the tangent line was horizontal. In other words, the derivative was 0. Similarly, for functions of two variable, the tangent plane is horizontal in both cases. And, whoops, yeah. Let's see what that means. So we'll say the tangent plane is horizontal at local extrema. So an extreme, an extremum is either a local min or a local max of a function. So it can be either. Extrema is just the plural of that. So a local mins and local max is the tangent plane is horizontal. Well, we know the equation of the tangent plane is, so suppose it happens at AB. So it's f of AB plus the partial of f with respect to x at AB times x minus a plus the partial with respect to y at AB times y minus b. So if our tangent plane is horizontal, that means it's going to be parallel to the xy plane, right? The xy plane is the plane z equals 0. So every plane parallel to z equals 0 is just z equals a constant. So if our tangent plane is of the form z equals a constant, that means if we look at the equation of our tangent plane, that means the partial of f with respect to x has to be 0 and the partial of f with respect to y has to be 0. So let me see. So if there's a local max or min at our point AB, then both partial derivatives are going to be equal to 0. So let me put this in a theorem here. In fact, it could be that the partial derivatives also don't exist. So for instance, if we have a function of one variable, remember we could have a local min or local max at sort of a cusp here. And in that case, at a cusp, the derivative just doesn't exist there. So you can have a local extreme value if the partial derivatives, one or both, don't exist also. So, oh, sorry, let me define what these guys are. So we say a point is a critical point, just like for functions of one variable. So it's a critical point for a function of two variables. If the partial derivative with respect to x is equal to 0, or does not exist, and the partial of f with respect to y is 0, or does not exist. Whoops. So for either both partials are equal to 0, or one is equal to 0 and the other does not exist, or both don't exist. But for both partials, They either have to be equal to 0 or not exist. So our theorem is that if a point AB is a local extremum, in other words, if a local max or min happens at AB for a function f of xy, then that point is a critical point for f. Let me say critical point of f. So this is useful because it tells us if we want to find critical points, we know how to find them. So to find a critical point, we know if it's a critical point, it has to be, oh, sorry. If it's a local max or a local min, it has to be a critical point. So if we want to find a local max or min, we look for all the critical points, and it's got to be any local max or local min has to be one of the critical points. So we're looking for local maxes and local mins. We're going to find the critical points of a function. So for example, let's find the critical points of the function f of xy is 11x squared minus 2xy plus 2y squared plus 3y. That's our function. Okay, so we're going to find all the points x, y where both partials are equal to 0. Technically, it could also happen where one of the partial derivatives is does not exist. That's not as common, but it can happen. And if we come to an example, I'll highlight that. But in this case, you take the partial derivatives. There's nowhere where the partials don't exist. So we need to find the points where both partial derivatives are equal to 0 at the same time. In other words, we're finding the critical points. So what we do is we take the partial derivatives. So the partial of f with respect to x, so 11x squared becomes 22x, minus 2xy becomes minus 2y, 2y squared becomes 0, 3y becomes 0, and we set it equal to 0. And we look at the partial of f with respect to y. So 11x squared becomes 0, minus 2xy becomes negative 2x, plus 2y squared becomes plus 4y, and then 3y becomes 3. And we set that equal to 0 also. Okay, so there are lots of different ways this could shake out, ways you could solve this, but usually it comes down to like one of two things. Usually one of each of the equations, or maybe for each equation, usually you can either, it'll either involve just one variable and you can solve for that variable directly from that equation, or you can get a relationship between the two variables in that equation, right? You can say one variable is equal to something in terms of another variable. So for instance, for this first one, and then you use that relationship in the next equation to solve for one of the variables. So for the first one, 22x minus 2y equals 0. In other words, 22x bringing 2y over the other side is equal to 2y, or dividing both sides by 2, so we can get y by itself. Y is equal to 11x. So we don't know what x and y are specifically yet, but we know at all the critical points, the y value has to be equal to 11 times the x value. And we're going to use that relationship in the next equation to solve for x. Can you also cancel out one of the variables? Sometimes. Sometimes you can, but for instance, we could have like y is equal to like square root of x or something like that. So if it's just like two linear equations, you can, but you can't always do that. But you could in this case, Nick. But like if it's like y is equal to x squared or square root of x, then you wouldn't be able to do that. Yeah. I would say this is like the easiest way to do it. And you can just use this for any problem, this sort of approach. So we're going to use that relationship in the next equation. We're going to, every time we see y, we're going to sub in 11x. And when we do that, we get negative 2x plus 4 times y is now 11x plus 3 equals 0. In other words, so negative 2x plus 44. So we get 42x. That's beautiful. Is equal to negative 3. So we know x has to be equal to negative 3 over 42, which is negative 1 over 14. Okay, so we know the x value, and we also know, so there's only one x value that works at the critical point. And we know at the critical point, y has to be equal to 11 times x. So we use that relationship. So we know y is equal to 11 times negative 1 over 14, negative 11 over 14. So our only critical point is negative 1 over 14, negative 11 over 14. X is negative 1 over 14, y is negative 11 over 14. Okay. Right, so there could be any number of critical points in your equation, but this one happens to only have, for your function, this one happens to only have one. But does everyone understand how we found the critical point there? We just set both partials equal to 0, and either you can solve directly for one of the variables from one of the equations, or you can get a relationship between x and y and then make that substitution into the second. to solve for one of the variables. Okay, so if we look at the graph of this, let me go ahead and show you what this looks like. Oops, okay. So if we look at the graph of this guy, it is in fact going to be a local min. So this is the point where it happens. It's a local min of our function. We don't immediately know how to tell that it's a local min from the equation, but it is a local min, and it's obvious when you look at the graph. We'll talk about that in just a second. Okay, so let's quickly look at another example to show that not all critical points are local maxes or local mins, though. So this one would be really easy to find the critical points of. So our function is going to be y squared minus x squared. And in fact, it's so easy, I will let you guys find the critical points really quickly. Is there a way to check algebraically if it's a critical point? I mean, that's what we just, you mean like from the function? Like without looking at the partial derivatives? Nick?
I just meant like if you were like you showed us like on the actual graph in Achieve, like I meant if there was a way, because you said like not.
Oh, to tell whether it's a local min or a local max?
Yeah.
Yeah. That's where we're gonna show. I'm gonna come to that in just a sec. Yeah.
Okay.
Yeah. But I'll go ahead and find the critical points of this function, and then we'll look at whether it's a local min or a local max or neither. Right, so it turns out the only critical point here is going to be 0, 0, because partial with respect to x is negative 2x. So set that equal to 0. That means x has to be equal to 0 at a critical point. And our partial with respect to y is 2y. Setting that equal to 0, that means y has to be 0 at a critical point. So 0, 0 is going to be our only critical point. So let's look at the graph real quick. My beautiful, beautiful graph. And we'll see that it's actually neither a local min nor a local max. So this is a hyperbolic paraboloid, rather. So it's sort of a saddle looking thing. Actually, let me. So what happens, 0, 0 is our critical point. So it's kind of hard to see what's going on from the picture, but if we sort of go along the x-axis, 0, 0, the value of that is 0. So if we go along the x-axis, what's happening is if you move along the x-axis, as you move away from 0, 0, the value of your function is going to be negative, right? You're sloping downwards away from 0, 0 as you move sort of in the direction of the x-axis. So 0, 0 is the highest point along the x-axis. What if we go along the y-axis? It's actually the lowest point, right? Our graph goes up as you move in the, along the y-axis. As you move in the y direction, all of the points go up. And so no matter how close you look to 0, 0, there are points where the value of the function is less than 0 and points where the value of the function are greater than 0. So it's neither a local min nor a local max. Even though it's a critical point. So critical points can be local mins, local maxes, or neither. And if it's neither, we call such a point where it happens a saddle point. Because if you look at this, it kind of looks like a saddle. Okay, so if you find the critical points, those points can be either local mins, local maxes, or saddle points, which is neither local mins nor local maxes. So how do we tell without graphing? Because you're rarely going to be able to graph these guys. Whoops. So the way we do that is we have a second derivative test for functions of two variables that works similar to the second derivative test for functions of one variable. That'll tell you whether a critical point is going to be a local min, a local max, or neither. Okay. So the thing we're going to be checking is called the discriminant. So the discriminant of f of xy, we'll call it capital D. So that's going to be, it's going to involve all the second partial derivatives. So it's going to be f sub xx times f sub yy. So both of the, I guess the same partials, right? fxx, fyy, where both partials involve the same variable, minus the mixed partial squared, f sub xy squared. This is gonna be the guy we're gonna be looking at. So another way to remember this is we can look at a determinant. So suppose along the top row, we look at, so if we look at the top row and the bottom row, along the top row, we're taking the partial with respect to x first. And along, so the rows tell you what partial you take with respect to first, and the columns tell you what partial you take with respect to second. So in the second column, we take the partial with respect to y. Those tell you, whatever. I'm sorry. So the columns tell you what you take the partial with respect to first, and the rows tell you what you take the partial with respect to second. Doesn't matter. Just look at what I'm writing here. And then we take the discriminant of that guy, or the determinant. right? So multiply the diagonals together, subtract the off diagonal from the main diagonal. So we get fxx times fyy minus fxy times fyx, but we know by Clairaut's theorem, those are equal. So those are both fxy squared. Sorry, if that made no sense to you, ignore it. Just remember the fxx fyy minus fxy squared. That's the discriminant in this case. Okay. So here's how the second derivative test works. So suppose we find a critical point. For our partial, or sorry, for our function f. So technically this is assuming all the partials are continuous, but that's basically always going to be the case in this class. So if let me write it this way. So if the discriminant is positive, right? So if we plug in AB into our discriminant, fxx AB times fyy AB minus fxy at AB squared. So if that thingy is positive, then it's either a local min or a local max. So then we need to check the second partial, f sub xx. So if it's positive, the discriminant, and fxx is also positive, then we have a local min at AB. In other words, f of AB is the local min value of the function. So similarly, if the discriminant's positive, and then we check fxx and see that it is negative instead, then we have a local max. So we check our discriminant and we see that it's positive. So if your discriminant's positive, you have either a local min or a local max. To see which one it is, you check f sub xx. In fact, you could check f sub yy also, and it would do the same thing, but that's neither here nor there. So in that case, now it works kind of like the second derivative test for functions of one variable. Remember, if your second derivative is positive, you're concave up, and so you have a local min. Similarly, if f sub xx is positive, then you have a local min. And if your second derivative is negative, you're concave down, and so you have a local max. In this case, f sub xx is positive, or sorry, negative, then you have a local max also. So discriminant positive, then you have a local max or local min, then it works like the second derivative test. Positive means local min, negative means local max for f sub xx. If you check the discriminant and you see that it's negative, then we know we have a saddle point. No need to check f sub xx in that case. And this won't tend to happen for the stuff we're going to give you, but it could turn out that the discriminant is 0. In that case, it's inconclusive. It could be anything, local min, local max, or neither. So I could come up with an example where the discriminant is 0. And I could come up with an example where it's either a local min, or an example where it's a local max, or an example where it's neither. It's impossible to tell, but usually that's not going to happen. But remember, if the discriminant's positive, it's either a local min or a local max, then it works like the second derivative test for functions of one variable. If f sub xx is negative, then it's concave down, so you have a local max. If it's positive, concave up, then you have a local min. And if the discriminant's negative, then you have a saddle point. Any questions about that? So yeah, just remember, discriminant is the similar partials multiplying together minus the mixed partials squared. Oops. Oh, we love it. Whatever. Okay.
Right, the fxy is right the derivative of f with respect to x and then y, correct?
Right. Yeah, it's the same as fyx also. But yeah, take the partial with respect to x and then the partial with respect to y. Okay, so let's do an example really quickly. Why are you like this? Okay, so let's find and classify the critical points of the function f of xy is going to be x cubed plus y cubed minus 12xy. So find and classify the critical points means, well, find the critical points. And then for each of those critical points, do the second derivative test to see whether it's a local min, a local max, or neither. So the first order of business is finding the critical points. So to do that, we set both partials equal to 0. I'm going to go through this rather quickly. So the partial of f with respect to x is going to be 3x squared plus 0 minus 12y. So we set that equal to 0. The partial with respect to y is going to be 0 plus 3y squared minus 12x. And we set that equal to 0. Okay. So we can't directly solve for x or y from either of these equations. So we're going to have to get a relationship between x and y and then substitute into the second. So from this first equation, we're going to get x by itself, or sorry, y by itself. So we add 12y to both sides and then divide both sides by 12. We get y is equal to 3 over 12, which is 1 over 4, x cubed.
Why is it x cubed?
Squared, right?
X squared, you're right, I'm sorry. X squared. Thank you. So we're going to sub that in for y down here. Oh my goodness, dude. Okay. When we do that, so we get 3 times 1 over 4 x squared quantity squared. So that's 3 over 16 x to the 4 x squared squared minus 12x equals 0. And so we can, wait, I believe that's right. Yes, yes. Okay. So, okay, so I'm gonna, right. I'll just divide both sides by 3 in this case. Sorry. So 1 over 16 x to the 4 minus 4x is 0. And then I'm gonna factor this. So I can pull out an x. And I'm gonna pull out 1 over 16. So in other words, so I get x cubed minus, and then when I multiply 4 by 16 by the reciprocal, we get 64. And so from this equation, I see either x is equal to 0 or x cubed minus 64 is equal to 0. In other words, x is equal to 4. So if x is equal to 0, we know y is equal to 1 over 4 x squared. So what is y equal to in that case? Well, sorry, let me just tell you. It's equal to 1 over 4 times 0 squared, which is 0. So that's one critical point corresponding to x equals 0. And the other critical point is, well, we know x can be equal to 4. So when x is equal to 4, y is equal to 1 over 4 times 4 squared. 1 over 4 times 16 is 4. So these are our two critical points, 0, 0, and 4, 4. Right, so we got a relationship between x and y, subbed it into the equation, the other equation, solve for one of the variables, and then use the original relationship to figure out what the other variable was. Okay. So now, we're going to use the second derivative test, and I'm going to go through this really quickly. So remember, f of xy, x cubed plus y cubed minus 12xy. And we said the partial of f with respect to x, 3x squared minus 12y. And the partial of f with respect to y was 3y squared minus 12x. Okay, so we need to find fxx, fyy, and fxy. Well, fxx is going to be, so we take the partial of f with respect to x, take the partial of f with respect to x again. So 3x squared minus 12y, take the partial with respect to x, we get 6x. fyy, take the partial with respect to y, and then take the partial with respect to y again. 3y squared minus 12x becomes 6y. And then f sub xy, take the partial of f with respect to x, and then take the partial with respect to y. So we get 3x squared minus 12y becomes negative 12. So the discriminant is fxx, oops, which is 6x times fyy, which is 6y, minus fxy squared so we got 36xy minus 144. And let's check the discriminant at each of our points. So the discriminant at 0, 0 is going to be 36 times 0 minus 144. So the discriminant at 0, 0 is negative. So we have a saddle point at 0, 0. Now if we check it at 4, 4, so we get 36 times 16. And so we get 576 minus 144, clearly positive. So our discriminant's positive at 4, 4. So now we need to check the partial of f with respect to f sub xx at 4, 4. So f sub xx at 4, 4 is 6 times 4, which is 24, which is positive. So the discriminant's positive. We know it's a local max or local min. So we need to check f sub xx there. We see that f sub xx is positive. And so positive is like concave up in this case. So we have local min. At 4, 4. Sorry, I went through that really quickly and still managed to go well over. My apologies. But that is how we do that. We got to find the critical points, and then we do the second derivative test at those critical points. Any questions? My apologies for going over. That took a lot longer than I expected. Okay, so that's local mins and maxes. We'll talk about absolute extreme values and how to find them on Wednesday. So I'm going to go over to the office hours Zoom, and I will see y'all either there or on Wednesday. Have a good one, guys.